Hello, my name is Kevin Laura, and this is my circular motion project. So, obviously, I enjoy hitting nukes and making phenomenal plays behind the dish, but the small and minor aspects of technique is what wins games. Everything in baseball is related to physics in some type of way, whether it is circular motion or projectile motion. Not one thing in the sport opposes the laws of physics. One of the most technical parts of the game includes throwing the ball. Throwing, whether over or underhand, is related to circular motion. Although more prevalent in softball, it is capable of being related to baseball. For example, in the video, when throwing long toss, I am forced to do a perfect circle with my arm in order to extend and bring the ball further. However, the most intriguing part of the entire process is the fact that, similar to circular motion, wherever I release the ball, it follows a tangential line from the circle. In the next example, I'm doing it underhand, and for the same reason, it propels tangentially from the circle. This event is created due to a centripetal force directed to the center of the circle. The centripetal force is derived from Newton's second law, F equals ma. However, is manipulated to be Fc equals mac, m being mass and a being acceleration. Acceleration in this case does not represent an increase in speed, but a change in direction. Since an object's speed remains constant, it does not necessarily mean the velocity is constant, since there is a change in direction. With a change in direction, there's an acceleration. For the first example, I was able to obtain the acceleration through the equation v squared over r. And in order to find v, I use the equation 2 pi r over t. I use a meter stick to determine the length of my arm, and in this case the radius. A video program to perfectly time the seconds it takes to complete one revolution. Using this, I was able to determine the tangential velocity, and with this calculation, I was able to plug it into the acceleration equation, which resulted in a value in meters per second squared. I finally plugged it into Newton's second law to obtain a force. My arm had a mass of about 10 pounds, however, when converting it to kilograms, it was about 4.53592 kilograms. Although I was able to calculate all these things solely using a mass scale, meter stick, and iPhone, the main aspect of the problem was the velocity, as it conveyed the fact that depending on where I released the ball, it follows a strong tangential path away from the circle. After the release point, it is practically gravity's job now to bring the ball back to ground level, and that is caused by projectile motion, as gravity is the main force causing it to fall. Obviously, in circular motion, it depends on horizontal or vertical circles, and in this case, throwing a ball is a vertical circle. So gravity is not negligible in this situation, except for in the two middle points where the equation would be F equals mac. In this case, since my arm would provide, tension to the ball, the top would be a different equation from the bottom because gravity is working together at the top. So that would be the weakest point of tension or normal force, depending on how you look at it, because I'm gripping the ball. But the top, it would be Ft plus mg equals mac. At the bottom, it'd be Ft minus mg equals mac, because at the top they're working together to go downward, at the bottom they're working oppositely. Baseball is something that could really be applied to circular motion, as every single arm motion, every single movement can be considered a part of circular motion. When throwing the ball, it solely depends on where you release it. If you release it all the way up here, you'll sail the ball up. It follows the same aspects in circular motion, where if you release it here and it's moving counterclockwise, so in this direction, but on the screen it's probably moving clockwise, I don't really know, but in this case it would shoot up. If it was moving clockwise at this point, it would shoot right downward. This is the same aspect with baseball, as if I were to throw it straight at the point after going in a complete circle right here, it will follow a straight path. But if I release up here, like I said, I'll sail it. If I release too low, it'll go straight to the ground. So as you can see, there's many aspects of baseball that's related to physics, and there's many laws in place that go in line with many of the events that occur in a baseball game, whether it is throwing a ball, hitting a ball with a bat, anything. It's often related to physics. So thank you for watching.